In this video, I want to have a look at the properties of inverse trig functions. So just to jog our memory, I've got our three graphs here. And the first thing that I want to have a look at is symmetry. So looking to see whether these graphs have odd symmetry, even symmetry, or neither. So hopefully just by looking at the graphs, you can see that sine inverse and tan inverse are both odd functions. They both have that rotational symmetry about the origin. So we write that like this here. Cos is a little bit trickier though. It doesn't have, I guess, traditional odd symmetry, but it does have that rotational symmetry about this point here. So it has odd symmetry about its y-intercept. The way we write that is like this. Now that's not very intuitive, so we are going to go through and prove it. So we're going to start using that left-hand side. We're going to write let alpha equal that left-hand side, so cos inverse of minus x. Now what that means is that we can rearrange it so that we end up with cos alpha is equal to minus x, but that only holds when alpha is between 0 and pi. Now we can rearrange that to make x the subject, so we'd have x equals minus cos alpha. And we don't know that minus cos alpha is equivalent to writing cos of pi minus alpha. Now you can tell that by looking at the graph of cos as well if you need to jog your memory on that. Alright, so we now have this equation here. If we rearrange that again, we'll end up with cos inverse of x is equal to pi minus alpha. If we rearrange that to make alpha the subject, we'd end up with alpha equals pi minus cos inverse of x. So that's bringing the alpha over to the left-hand side and the cos inverse x back over to the right-hand side, which is what we wanted, what we had written up here. All right, so that's having a look at symmetry. The second thing I want to have a look at is this identity that sine inverse plus cos inverse is going to equal pi on 2. So let's have a look at proving that. We're going to start by letting alpha equal cos inverse of x. Now, if we rearrange that, then we can have cos of alpha is equal to x, but that's only when alpha is between 0 and pi. Now, we know that sine and cos are complementary angles or complementary functions, so that means that cos alpha would be equivalent to or equal to sine of pi on 2 minus alpha, so that's going to be equal to x. Now, if we can rearrange this back into an inverse function instead, we'll end up with pi on 2 minus alpha is equal to sine inverse of x. Now, we can do that because we know that this whole section here, this pi on 2 minus alpha, we know that that's going to lie within our between minus pi on 2 and pi on 2, which is what we need for sine inverse. And we know that because alpha sits between 0 and pi. So it is still within that range, so we're still okay to do this. So now if we rearrange this a bit, we can end up with sine inverse of x plus alpha is equal to pi on 2. But if we have a look back at what we started with, letting alpha equal cos inverse of x, then this is going to become sine inverse of x plus cos inverse of x is equal to pi on 2, which is what we wanted for that identity. The last thing I want to have a look at is composite functions. So if we have a function f of x, then generally if we take f of f inverse of x, that's going to spit out x, what we started with, because one's undoing the other. And it works the other way as well, generally, that if we take the inverse of the original function, then we're going to end up back at x as well. But it doesn't always work out because there can be restrictions on the domain. So there can be values of x where this won't work. So we want to have a look specifically with our trig inverse functions. So if we have a look first where our inverse function is the inner function, so for example, sine of sine inverse, cos of cos inverse, or tan of tan inverse, then those will all spit back out that original number that we put in. For tan, it's no matter what that x value is. But for sine and cos, it's only when x is between minus 1 and 1. And that's because this inner function, the sine inverse and the cos inverse, aren't defined outside those values. So if you tried to substitute anything lower than -1 or above 1 into sine inverse or cos inverse, that would be undefined. You'd get a math error on your calculator. So if this inner function is undefined, then we can't take sine of something that's undefined or cos of something that's undefined. So it only works for these values. And if you want to give that a try, you can set yourself up a table of values. You can pick some x values, pick some below -1, above 1, and pick some in between as well. So you might go say -2, -1.5, 0, 1.5. You can do more in between there as well if you want. Then you're going to do sine inverse of x. So what it's sine inverse of whatever this number is, and then sine of that sine inverse. So you'll take sine of whatever you got in this second column. And what you'll end up with is for anything outside -1 and 1, it'll be undefined. For any of the values that you put in here between 1 and -1, then when you get to the end, whatever the number was in this first column, it will be exactly the same in the last column. So what that looks like in a graph is this. So we've got our sine, and it's going to be y equals x. So this is just going to spit back out x. So it's going to be that, but only between -1 and 1. Cos will be exactly the same, and tan will be that same line, but it isn't restricted. So it is for all real values of x. If we have a look at these the other way around, where we've got our inverse function on the outside, so in this one we've got sine inverse of sine x, it's going to be a bit more complicated. So what I do want to do this time is go through a table of values and see what happens. So we're going to look at a table of values for our sine case, but it will work the same for our cos and our tan, or similarly for our cos and our tan as well. All right, so what I've drawn up is a table with some x values filled in all the way from -2 pi to 2 pi. Then I've got my sine x and then my sine inverse of that value. So you can go through and fill this in. We'll do the first ones together. If I do sine of -2 pi, I'll end up with 0, and then sine inverse of 0 will give me 0 as well. If we do a different one, let's say pi on 4, so this one here, if I do sine of -pi on 4, that's going to give me -1 on root 2, and then sine inverse of -1 on root 2 will give me back -pi on 4. So we'll go through and fill in the rest of that table in the same way, and then have a look at the results. Okay, so if we have a look at those, what you can see is that within these ones here, the values at the end are exactly the values that we started with. So that's why we end up with sine inverse of sine x equals x within those values of x, so between -pi on 2 and pi on 2. But it does still give us values outside of that. When we did the last ones, it was undefined outside those values of x. This one is still defined, it just doesn't follow this relationship. What it actually ends up looking like if we graph it, if we get rid of that one, is this. So we can zoom out and we can see that that goes on forever. So between the values of -pi on 2 and pi on 2, it is still y equals x. This will still simplify to give us the value that we put in. But outside of that, it doesn't follow that relationship, even though it is still defined. Now, if we went through and did the same sort of thing with a table of values for cos, we would end up with a graph that looks like this. So it is still y equals x between 0 and pi. And if we did it for tan, it would look like this. So it is still between that -pi on 2 and pi on 2, that it holds that, that this will equal x. All right, so that's having a look and proving some of the properties of inverse trig functions.